Industrial manufacturing requires a massive, reliable water supply to maintain continuous operations. But as severe droughts and shortages become more frequent, that continuity is threatened. This threat is particularly acute in Thailand's central and northeastern river basins, regions where water scarcity has escalated from a seasonal nuisance to a strict operational constraint. To understand how companies are surviving this stress, researchers conducted a comprehensive census of 120 specialized industrial factories operating at the frontier of water management. The researchers measured water use efficiency across 4 dimensions: minimizing operating costs, maintaining water quality standards, optimizing extraction quantities, and the responsiveness of management operations. The prevailing assumption is that hitting high marks across all 4 dimensions is just a matter of strategic choice. It is assumed that if a management team is committed to gradual trial and error, they will eventually become highly eco-efficient. The data from these 120 factories proves otherwise. Efficiency is a rigid structural capability, largely independent of management's behavioral intent. This aligns with the resource-based view of economics, a framework arguing that a firm's competitive advantage relies on the tangible resources it can actively deploy. The study reveals a strict, unavoidable threshold. Advanced water use efficiency is virtually impossible unless a factory crosses a highly specific, measurable baseline of capital and human resources. To accurately predict whether a factory will survive the next major drought, we have to stop analyzing their plumbing and start examining their balance sheet. To find the root cause of efficiency, the researchers had to isolate structural determinants from everyday behavioral management strategies. This diagram shows the study's conceptual framework. The team tested 6 structural variables: registered capital, workforce size, years of operation, ownership nationality, factory location, and industrial sector. This table summarizes the statistical variance. We can eliminate the factors that do not statistically impact efficiency. The p-values for operational age and foreign ownership fall above the 0.05 significance level, meaning neither has a measurable effect. This debunks a major industry myth. A factory that has been operating for 20 years is not inherently more efficient than a 5-year-old plant. Experience alone does not substitute for deployable financial and organizational capacity. Even the geographic location of the factory within the studied basins yielded no significant variance in performance. However, 2 factors did cross the statistical threshold for high significance: registered capital with a p-value of 0.007 and number of employees at 0.003. Because operational time and corporate origin do not dictate environmental performance, survival in these water-scarce basins relies on raw, quantifiable scale. While the initial analysis proves that scale matters, we need to run post-hoc least significant difference tests to reveal the exact architecture of this resource constraint. This table breaks down those pairwise comparisons, specifically detailing how different tiers of registered capital perform against one another. When translated into a visual model, the dense LSD data forms a clear, distinct step function. At the lower end, firms with under 50 million baht in capital perform significantly lower, but at the upper end of the graph, the performance gap vanishes. There is no significant difference in efficiency between medium firms and massive firms exceeding 200 million. By shifting the axis to the workforce size variable, we check if this pattern is consistent. The structural pattern is identical. Having fewer than 50 employees results in a performance drop, while crossing the 50-employee mark reaches the same efficiency plateau. The researchers also noted that industrial sectors under intense regulatory pressure, like food and beverage manufacturing, statistically outperformed service groups. This is likely due to their accelerated adoption of tech-enabled green value chains. Ultimately, industrial eco-efficiency follows a rigid step function logic. Superior performance remains out of reach until a firm amasses at least 50 million baht in capital and a workforce of 50 employees. What specific operational assets are accessible with a 50 million baht budget that a smaller operation cannot simulate? The answer lies in the operational realities of the 3 Rs: reducing, reusing, and recycling water at an industrial scale. This requires heavy physical infrastructure. High registered capital finances the acquisition of high-end filtration equipment and closed-loop recycling systems. Beyond hardware, it supports real-time IoT digital monitoring backed by a specialized workforce. Integrating this hardware and software creates a continuous feedback loop that drives down water extraction volumes and operating costs. This tightly woven synergy generates causal ambiguity. Competitors cannot easily copy the efficiency because it relies on a complex internal web of expensive resources. Small firms operating below the 50 million baht threshold are structurally excluded from this feedback loop. The initial capital requirements are simply insurmountable. Without overcoming that initial financial barrier, small factories are trapped in a cycle of linear water consumption, regardless of their environmental intentions. For the facility managers on the ground in these drought-prone basins, this data forces a shift in strategy. Medium and large factories have a clear mandate. They must lean heavily into their structural advantages. To maintain their position above the threshold, large firms should aggressively fund comprehensive reuse systems, advanced recycling tech, and continuous digital evaluation. The strategic reality for a small factory is entirely different. They must abandon attempts to mimic the capital-heavy systems of massive corporations. Instead, small firms should prioritize low-cost efficiency measures, behavioral changes on the factory floor, and incremental operational tweaks. To bypass their internal capital limits, small operators can seek out collaborative industrial estates, where heavy infrastructure is shared across multiple tenants. Accurate benchmarking requires peer-to-peer comparison. Judging a small firm's efficiency against a large firm's output ignores the fundamental laws of structural capacity. This dynamic exposes a critical flaw in current regulatory approaches. Blanket environmental mandates applied equally across a basin will inevitably crush small firms that lack the capital to comply. If the goal is basin-level water resilience, the state must step in to artificially bridge that 50 million baht gap. This starts with direct financial subsidies or tax credits specifically earmarked to help small factories install entry-level digital water monitoring systems. It also requires state-sponsored digital inclusion, ensuring that industrial zones have the robust internet connectivity required to run these new monitoring networks. Finally, governments need to provide specialized low-interest loans designed strictly to overcome the steep upfront costs of physical recycling hardware. These tailored, scale-appropriate interventions allow resource-constrained factories to simulate the technological readiness of massive corporations. Strengthening national water security depends on surgically funding capability where it does not naturally exist. Industrial eco-efficiency is an economic equation. To save the basins, every factory must have the structural capital required to balance it.